In this video, I want to talk about homogeneous systems of linear equations. So homogeneous is a fancy way of saying the right-hand side equals zero. So if you are working with differential equations or basically any situation in dynamical systems or whatever, you usually, if you're talking about homogeneous systems of equations, you're talking about ones that have a constant term equal to zero. So for us, what that means is that we're talking about equations that look like this, right? Where we have a coefficient matrix A, a variable vector, and the zero vector. So let's consider this example. So here we have a coefficient matrix, and just by the dimensions of the matrix, I know that my variable vector is going to look like this. And if I'm considering the homogeneous addition of this equation, I know that the right-hand side is going to be the zero vector. So working backwards from that, I can write down that system of linear equations, and I see exactly what I'm looking at is a system of linear equations where all of the constant terms are zero. The interesting thing about this class of systems of linear equations is that they always have a solution. So there's never any question about whether or not a homogeneous system of linear equations has a solution. It has always at least one solution, and it can have infinitely many solutions. So if we want to think about what that solution is, let's just look at this system of linear equations, and maybe we can extrapolate from that. There's a trio of numbers, right, an ordered triple that I know for sure when I plug in the values here, I'll get zero. And if I plug in the values here, I'll get zero. And that trio of numbers, that ordered tuple, is just the zero vector. So in this case, a three-dimensional homogeneous system of linear equations has the origin as a solution. And of course, sometimes we're not in 3 dimensions. So however many dimensions you're looking at, however many variables you have, you can have the zero vector of appropriate dimension. And that's always going to be a solution. So let's just take a minute to think about what that means. Remember, each one of those linear equations is describing a line or a plane or a hyperplane in some space of some certain dimensions. And what this is telling us is that if we have a right-hand side equal to zero, our constant term equal to zero, that means that our plane goes through the origin. And if we have a system where all the planes go through the origin, then the origin is a point that they all have in common. So it's a solution to the entire system of equations. So in other words, these two planes intersect in, well, two planes are going to intersect in a line, right, if they intersect at all. But if these two planes intersect in a line, that line is going to contain the origin. So in our more general situation of non-homogeneous systems of linear equations, and non-homogeneous just means not homogeneous, this right-hand side vector can be anything. So that means that this plane that's described by each line, each equation in your linear system could go through the origin or not. It just totally depends. And in general, as we already know, anything can happen with a solution like this. And the anything choices are 0, 1, or infinitely many solutions. In some situations, though, if we know some little bit more about the system of linear equations, we can say something more definitive. In particular, what's interesting for us right now is that if we know something about the homogeneous version of such an equation, then we'll be able to say something about the non-homogeneous version. So let's think about the homogeneous case as a comparison, right? So if we have AX equals 0. Now in this case, this is a linear system being described, and it's the solution set is some set of points that contain at least the origin. So it's some set of 3 or more planes and 3 or more dimensions that intersect at least the origin. And it's possible that they intersect in more than one place. If they intersect in more than one place, then they have to intersect in infinitely many places. So let me just draw an example of something like that. Okay, so I'll let you stare at this for a second, but what I want to point out is that this is a situation where we have three planes in that pages of a book configuration. So they actually intersect all three of them along a line, and the origin is one of the points on that line. So this is a homogeneous system of linear equations, and it has infinitely many solutions. And those are the two possibilities, right? We always have at least one solution in the homogeneous case, and that's the zero vector. And we may have infinitely many, right? If we have more than one, we'll have infinitely many, but there's no way that a homogeneous system fails to have a solution. Okay, so if we know that our homogeneous system can have one and exactly one of these two configurations, right? There's no way it doesn't have a solution. Let's think about what happens when we replace this zero with an arbitrary vector b, right, with non-zero entries. Well, changing the right-hand side of an equation of a plane, all that can do is move it back and forth in space, but it can't tilt it in a different direction. So if you can imagine these three planes intersecting in a point and moving one of these planes around. Now remember, I can't tilt them in a different direction because I'm only changing the constant term. So let's think about it, right? If I move the planes, let's say I move them all in the same direction, the same amount, right? I just shift this whole system up or down. Well, that's really exactly what we are doing, right? Whatever that b vector is, we take that, we use that to shift around all three of those planes the same way, and we just get another solution to our linear system. In a case like this, we might, by changing the right-hand side, we might end up with still a solution. But imagine now, like, keeping, say, the orange one and the green one in the same place, and then moving this purple one way up high. Well, now there's no points in common of all three of these planes. So in this case, in the case where our homogeneous system has exactly one solution, the more general non-homogeneous system may have exactly one solution or it might have none, but it can't, because the planes can't tilt in different directions, we're not going to be able to change the set of intersection points into anything other than anything more than a point. Now, in this other case, where our homogeneous system has infinitely many solutions, what happens when we start moving these planes around? Remember, when we're changing the right-hand side, that constant term, we can't tilt the planes in different directions. All we can do is like move them back and forth in space. We can't change their tilt with respect to the coordinate system. So if I move one of these planes, say the blue one around, then I could move it so that instead of this line being here, it's down here. And I see that like that would make it so that there are no points in common to all three lines. I'd get that tent-like configuration that we talked about a ways back. So it's possible if I go from my homogeneous version to my non-homogeneous case, when in a situation where my homogeneous system had infinitely many solutions, that I'll actually get no solutions. But it's also possible, so just now imagine taking this whole picture and moving it up or down or left or right. It's also possible for me to have a non-homogeneous situation with the same coefficient matrix that has infinitely many solutions. So when our homogeneous system has infinitely many solutions, again, we could have zero solutions in the non-homogeneous case, or we could have infinitely many solutions. But because we can't tilt these planes in different directions, we're never going to be able to get exactly one solution.